Hello class, welcome to day 20 of Coronachem. Today's class we're going to learn about voltaic cells and we're going to cover the homework I assigned yesterday and then I'll give you a few little exercises you can try on your own. I would recommend you also to continue watching the playlist called Electrochem. Yesterday I assigned you to watch parts 4, 5, and 6. I would now recommend you go and watch the ones after part 6. Watch the whole playlist if it helps, especially if you're having trouble understanding some of the steps in the chapter. Watch it all from the beginning because all the notes for the whole chapter are contained in those playlists. And it doesn't hurt to repeat stuff. You'll understand it more clearly. So what is a voltaic cell? We've established from past lectures that a redox reaction is the coupling of two reactions, a reduction and an oxidation. And we talk about half reactions because both reactions can be taking place in separate compartments, and that's how we can harness the electrical exchange that takes place. Electrons are exchanged from one reaction to the other, so one substance is being oxidized while the other substance is being reduced, and that takes place through the exchange of electrons. By separating the two half reactions like we do here in two separate beakers, we can force, by connecting the two electrodes, these are electrodes, these are pieces of metal dipped into the solution, we can force the electrons to pass through a wire, and because the electrons have a certain amount of energy, which we measure as voltage, the electrons can be made to do work. And that's how we make a battery. A battery has essentially two reactions that are somehow separated by a membrane, and the electrons are forced to go from one side to the other. They always travel from the anode to the cathode. So the plus and the minus side of the battery. So what can I say about this? On the left side, you always have the anode. A good way to remember how to set up a voltaic cell is you always put the anode on the left and the cathode on the right. So it's always alphabetical, anode, cathode. Another way to remember is that the anode is oxidation, the cathode is reduction. You'll see that both start with a vowel for anode and both start with a consonant for cathode. So anode oxidation, cathode reduction. Then we talk about the metal. On this side we have zinc, on this side we have copper. Now if you go to the back of the book, which you don't have, you could look up the oxidation potentials or the reduction potentials on the internet. I'm sure there are lists available for anybody who does a brief search. Look up reduction potentials, you'll have a list. Usually they're listed as reduction potentials. They always show the ion having electrons added to it and turning back to the elemental state, and then they'll write a voltage next to it. If the thing has a positive voltage, it means the reaction tends to happen in that direction. If it has a negative voltage, it means the reaction tends to go the other way. Okay? And typically whenever you have a redox reaction, you can have two positive reactions, you can even have a positive and a negative, but for the reaction to go forward, you have to have a positive voltage overall. Typically what will drive the reaction forward is the one that has the more positive potential. So whichever part of the reaction has a more positive potential will drive the other one either backwards if it's necessary, or they'll both go forwards if they both have a positive voltage, then you'll add the voltages. The way these reactions are written, and a good way to keep this in mind is to think of the activity series. The elements at the top of the activity series, like lithium for example, like to give away electrons, whereas elements at the bottom of the activity series prefer to accept electrons from other more active metals. And typically what you'll have as electrodes in a voltaic cell is metals, because other things don't conduct electricity. So to be able to construct a voltaic cell, you need to have something that conducts electricity. You can't just put a piece of sulfur in the in the solution, because the sulfur doesn't conduct electricity, you won't be able to do anything with that. So you have pieces of metal like zinc. They sometimes even use graphite as electrodes if they want something that's non-reactive. So in this case, in this voltaic cell, they have a strip of zinc on this side and a strip of copper on the other side. If you look at the reduction potentials that are listed in the back of the book, you'll see that the reduction of zinc, so taking zinc 2+ and adding 2 electrons to it to give you a zinc solid, has a negative voltage. So this reaction I wrote backwards to turn it into a positive. So it's positive when you write it as an oxidation potential. So that means it's a lot more likely to be the anode. And this one is positive when you write it as a reduction. So it's more appropriate to put it as the cathode. So these two reactions, when you combine them, this has 0.763 volts, that one has 0.33 volts, it adds up to a total of 1.10 volts. So these two are good metals for making a battery. In fact, the word for battery is named after a guy called Alessandro Volta. Alessandro Volta, an Italian chemist, took a little pile of zinc and copper, and he would put wet paper or cloth between the metals, and he made a little stack of these metal discs, and then he measured that it could create an electrical current. So it was a little pile, and in fact the word in Italian for pile is pila, which is also the word for battery. So that's where they got the word for battery. It's a pile, it's a little pile of metal discs, and that was the first battery ever invented. And from there they started doing experiments on animal legs. They would get the guy called Luigi Galvani, another Italian biochemist, discovered that you could make frog legs twitch by applying electricity from batteries. And I guess that's where we got the inspiration for the movie, for the book Frankenstein, where the mad scientist uses electricity to revive a dead body. So they had this idea in the 19th century that maybe if you apply electricity the right way, you can revive the human body. So obviously some wrong theories came out of that. If somebody's dead, it's because their soul is gone, so no amount of electricity is going to bring them back. Anyway, so these electrodes are dipped into a solution of sodium nitrate, or the appropriate nitrate of whatever salt. You can have zinc nitrate on this side and copper nitrate on that side. You'll see a little tube here connecting both solutions. That's called a salt bridge. And the reason you need a salt bridge is because on this side, on the anode, when the zinc reacts, pieces of the metal come off and go, little atoms of metal come off and go into the solution, and they abandon their electrons. So the electrons go this way, and the zinc ion goes into solution. And the electrons travel through the wire, they go to the other side, and they appear at the cathode. And what happens is the copper ions that are floating around in solution are attracted to the fact that there's negative charges in the, there's negative charges floating around, there's electrons floating around in the cathode, so the cations are attracted to it. That's why they call it a cathode. The cathode attracts cations, the anode attracts anions. I guess that's how they got the name. So the cations go towards those electrons, they combine with them, and the copper metal is deposited onto the cathode. So the cathode gets heavier and the anode gets lighter. This is a technique they use for refining gold and other precious metals. If you want to get really pure metal, have you ever noticed when they have gold bars, it'll say 99.999% pure? This is the technique they use for refining it. They use refining by electrochemical deposition of less refined gold to more refined gold, and they do it by cathodic deposition. And you get some very pure stuff if you pick your voltages just so. So what this salt bridge does is, because there's zinc ions appearing in solution here, the concentration of positive ions is increasing, and here the concentration of positive ions is decreasing. So you get a charge imbalance. If you don't have this bridge to allow ions of, say you put sodium nitrate solution in there, because a plus charge is decreasing in this side, what happens is the nitrate ions will move into the bridge and start moving this way into this solution to counterbalance the buildup of a negative charge. And on this side, because you have a buildup of positive charge, the sodium cations will start migrating into the bridge and going to the other side. So you get a net movement of ions. The cations will move towards the cathode. The anions will start moving towards the anode. If you were to take that bridge out, the reaction would stop very soon after that. So that's how the voltaic cell is represented. In a battery, all of that is comprised by putting a membrane to separate the two, but it's a porous membrane to allow for the migration of ions. All of that is wrapped up into a battery to create a self-contained cell. In a car battery, you have 6 such cells, each generating 2 volts, and because they're connected in series, they add up to 12 volts. If you were to connect the cells in parallel, you would get a battery that can generate 2 volts, but it would have a capacity to generate a lot more amperage. But now we're digressing. So how would you show the net equation of this redox reaction? You would show copper ions reacting with metallic zinc to give you solid copper, metallic copper, and zinc ions. And the voltage for that reaction would be 1.10. If you were to try to run the reaction backwards, the voltage would be reversed. You'd have negative 1.10, which means the reaction wouldn't happen. You'd have to actually drive it. You'd have to apply at least 1.11 volts to make the reaction go the other way. You'd have to do that with a charger. That's what charging a battery means. When you charge a battery, you're basically taking an external voltage, applying it to the battery, and you're forcing the reaction to go backwards by pushing the electrons into it. You can do that with some batteries. Some batteries you can't do that with, because if you try to run the reaction backwards, you get other reactions happening which can spoil the battery, or the battery doesn't accept it doesn't have an efficient acceptance of the reversal of the flow, and it starts to generate heat, and which can cause the battery to explode. So in some batteries it says do not recharge, because precisely because of that you'll end up blowing up the battery. Okay, next thing is we're going to look at the homework I gave you. I think the hardest part of this course is erasing the board. It just doesn't like erasing. All I do is manage to fade it a little bit, and then I got to clean off the rest of it using cleaners or solvents. I'm going to go buy a smart board today. Or not a smart board, but a proper whiteboard. This experiment of writing on the fridge is only marginally successful. Well, as they say, nothing ventured, nothing gained. You got to try stuff. Oh my, this is getting worrisome here. Try alcohol. 99%. Probably the best bet. I'm using the isopropanol, but I dropped the bottle and I broke the pump. So now I just gotta wipe it down with the stuff straight out of the bottle. Yeah, that works. Not as well as I would like, but it does work. Okay, that's as good as it's going to get for now. So let's look at the homework. On the homework I asked you to do 855B. Which looks like this. Chromic hydroxide, which is a solid, reacts with hypochlorite to yield chromate and chlorine gas. So the first thing to do is to separate it into half reactions. So we're going to show the chromic hydroxide first. So leave out the phases for while you're doing the calculation, just to make it easier and to have less clutter. And then you can reintroduce them at the end. So chromic hydroxide is turning into chromate, is your first half reaction. On this side you have 3 oxygens. First of all, let's look at the chromiums. 1 chromium on each side, so you're good. You don't have to worry about balancing that. Now let's look at oxygen. There's 3 oxygens on this side, 4 oxygens on the right side, so we're going to add 1 water molecule to balance out the oxygens, 1 H2O. Then we're going to balance the hydrogens. If you look on the left side, you have 3 hydrogens plus 2 hydrogens. There's 5 hydrogens on the left, 0 hydrogens on the right. So we're going to balance that by adding 5 hydrogens in the form of H+. Then the last step is to balance the charges. So if you look on the left side, there's no charges. And on the right side, you have a -2 and a +5. So the total here is +3. How do we bring it down so that this side has the same charge as that side? By adding 3 electrons on this side. So the 3 electrons will now both bring it down so that both of them are at 0. Let's see if it matches what I did yesterday on paper. And that is correct. The next step is to balance the hypochlorite into chlorine. So hypochlorite is turning into chlorine. So to balance that, you have 2 chlorines on the right, 1 chlorine on the left, so we're going to put a 2 in front of that so that you have the same number of chlorines. Now you're going to have 2 oxygens on the left, no oxygens on the right, so we're going to put 2 waters to balance that out. And now let's balance the hydrogens. There's 4 hydrogens on the right, 0 hydrogens on the left, so we're going to balance it by adding 4 H pluses on the left. Now worry about the charges. 2 -1s and 4 +1s means a total of +2. So +2 on the left, it can be brought down to 0 by adding 2 electrons on the left. Now both sides have the equal number of charges. You have 3 electrons here and 2 electrons there. So to add these equations so that they cancel out the electrons, you're going to multiply this one by 2, this whole reaction, and you're going to multiply this whole reaction by 3. That way you'll have 6 electrons going from this side and 6 electrons being taken from that side. So when you add those 2 reactions together, let me just double check before I lead you down the garden path. You get 2E, 2ClO, 4H+, 2CO2, 2H2O. Good. Everything checks out for now. The reason I don't trust myself is because even though I know what I'm doing, it's easy to make one little mistake and then it just spoils everything after that. So just be extra careful when you're doing these. I've burned myself many times because I lost my attention for 1 second and I forgot to put a minus sign somewhere, and then everything after that point is wrong. So it's very frustrating. Anyhow, 2 times CrOH3 gives you 2 CrOH3, plus 2 times H2O gives you 2 H2O, plus 3 times 2 electrons gives you 6 electrons, plus 3 times 2 hypochlorites gives you 6 hypochlorites, and 3 times 4 hydrogens gives you 12 hydrogens. That's just the left side. Now for the right side, I'm going to have to stagger it because there's not enough room on the fridge. 2 times chromate gives you 2 chromates, plus 2 times 5 hydrogens gives you 10 hydrogens, plus 2 times 3 electrons gives you 6 electrons, plus 3 chlorines, plus 6 waters. So there's your balanced equation. Obviously, we don't have a lot of room. We need a whole board to do this properly. So all this is over here. Imagine that. Okay. So the 6 electrons cancel. The 2 waters cancel with the 6 waters to form 4 waters on this side, and the 12 hydrogens on the left cancels out to give you 2 hydrogens left over on the left. So I'm going to put that over here. Okay. Now, I want to balance this equation in basic solution. So the way I'm going to do that, perhaps I should just rewrite it neatly so you can see what's going on. So I'll do that again. I'll just rewrite it here. Make sure I'm doing it right. So you get 2 chromates. I'm already wrong. You have 2 chromic hydroxides plus 6 hypochlorites plus 2 hydrogens yields 2 chromates plus 3 chlorines plus 4 water. So that's what our net equation looks like balanced in acid. But we want to balance it in base. So the way you do that, is you find the side that has the hydrogens on it, and you have the same number of hydroxides. So you're going to add 2 hydroxides here to cancel out these hydrogens. And of course, if you do it to one side, you got to do it to the other side. So we're going to do that here as well. So we're going to add 2 hydroxides over here as well to make everything balance out. These 2 will combine to form 2 waters. Conceptually, of course, not in reality, but this is a form of bookkeeping. It gives you the correct answer. This is not actually happening. It's just what we do to balance it. Okay? So now the 2 H2Os will cancel with the 4 H2Os, and you'll have a net 2 H2Os on this side. And now what you do is you rewrite the final answer with all the states of the different chemicals. So let's write our final answer now, our net equation. So 2 chromic hydroxides, solid, plus 6 hypochlorites, aqueous. Yeah, so the water's canceled. Gives you 2 chromates, aqueous. Please tell me I got the right charge on there. Yeah, I wrote -1. It's -2. -2. Yeah, that's not going to affect the results because the answer happened after I used the charges, so it's okay. It didn't carry through. 2 chromates plus 2 H2O liquids. Oh, and a 3Cl2, which is going to be gas. And did I leave anything out? Oh, the hydroxide. Plus 2 hydroxide. There's your balanced equation. Okay, does it match what I have in my book? Yes, 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 and yes. Okay, that's the correct answer. Okay, so there's your balanced equation using a basic solution. The next thing I had listed here for us to do, well, I'm just going to give you a teensy-weensy bit of homework. Okay, I'll give you the question from 738. Oh, that's not right. 2017. I'll give you the problem of 2017. I'll write it on the board so you can see what it is. 2017. No, better yet. 2019. 2019A. Okay, you can see it? Yeah. So 2019, this is your one homework question. Try to do it. If you can't do it, don't freak out. Just watch some of the more of the videos that I have posted, okay? But do watch them because you're only getting a half-hour class here. We're up to 24 minutes. So invest in your future. Remember, if everyone else is sitting at home doing fake homework, because it's very easy to get by with doing little or nothing. I don't know what the other teachers are doing, if they're laying on a lot of work or what. I'm trying to keep it about the same as what you would normally get when we're in class. So Don't get into that mindset of, oh, I'm not going to school, so I don't have to work. You do have to work. You have to work. This is your future. Think about it. Keep in the right mindset. You have to be disciplined because nobody's standing on your shoulders telling you what to do. You got to tell you what to do. Okay? So do it. Or else you come out of this with no education, and that would be no good. All right, so CR207. Chemistry for the blind. All right, so CR207. Aqueous plus I minus aqueous going to chromic CR3 plus aqueous plus iodate aqueous. Okay, so balance that in acidic solution. And I'll give you the answer tomorrow. Let's see if you can do it. All right, so I'll see you tomorrow, guys. That's all right. See you on Monday. So that's not a lot of homework for a whole weekend, but I got a lot of work myself. I got to finish correcting your tests. By the way, I'm about 1/3 of the way through correcting your tests, so by Monday I should have it all done. Okay, see you then. Bye-bye.